we discuss theorem 5.9. This theorem is the consequences of some theorems in chapter 2 and 1. First result is every ideal A of O with A not equal to 0 has a Z basis alpha 1 alpha 2 alpha n, where n is the degree of K. The second result, we have n of A is equal to the square root of the modulus of discriminant, and this discriminant is defined as discriminant of alpha 1 etc alpha n. This is the square of determinant of the matrix sigma I alpha j. The sigmas are the monomorphisms which maps each alpha 1 into its corresponding conjugates. So n of A can be computed using this formula. Okay, this is the theorem 5.9. We already discussed, you might have seen this result, O plus is in a free abelian group in chapter 2. And another result is the characterization of free abelian groups of rank n. O by A is finite if and only if this A is free abelian group of rank n. Here we already seen that this is finite, so we can get A plus A under addition is also a free abelian group of the same rank of O. So there is a Z basis, say alpha 1 alpha 2 alpha n, where alpha 1 alpha 2 alpha n is a basis for this A. Okay. This proves the part A. Every ideal A has a basis alpha 1 alpha 2 alpha n, Z basis. Now we can prove B part. For the B part, we assume a basis for O, and we already seen that alpha 1 alpha 2 alpha n is a basis for A. This is the basis for A, and we take W1 etc. Wn is a basis for O as well. Now you can write this, each alpha I is a combination of the elements of W1, W2 etc. Wn, say Cij Wj. Now we can easily get n of A is equal to, this is the norm, in fact this is O by A, which is equal to determinant Cij modulus of the determinant this. So this is nothing but theorem 1.17, so you can easily refer that theorem. Using this fact, you can write this result in theorem 2.7. Discriminant of alpha 1 alpha 2 alpha n is equal to determinant Cij square delta, that is discriminant W1 W2 etc. Wn. But we know that this n of A, norm of A, is nothing but determinant of modulus of determinant of J square. Then by taking square on both sides, you can replace this by n of A square. This proves the part B, because n of A can be written as square root of discriminant of alpha 1 etc. alpha n divided by discriminant of W1 etc. Wn. Okay, so this is what this discriminant is, nothing but the discriminant of W1 W2 etc. Wn. Okay, this proves part B. Hence the theorem. Now we have a corollary. If A is a principal ideal, then we can get, if this is the basis for O, then what is the basis of A? Base of A takes the form A W1 comma etc. A Wn. If this A is the ideal generated by A, this A is a single element. Now if we use this formula, n of A equal to n of this is the ideal actually, so that is n of the ideal generated by a single element A. So by definition, this is delta of alpha 1 alpha 2 alpha n, alpha 1 alpha 2 etc. are the Z basis for the ideal A. Here instead of alpha 1 we have A omega 1 etc. A omega n. So this will be A omega 1 or W1 etc. AWN divided by discriminant of W1 etc. Wn whole raised to 1 by 2. So this is the norm of this ideal. Okay. Now what is discriminant of AW1 etc. AWN? So that is the determinant of some matrix sigma I alpha j, that is alpha, instead of alpha j we have AWJ. So this is sigma 1 AW1 etc. sigma n AW1 again. Sorry, this is in fact sigma 1 of AWN. Then the second row we have sigma 2 AW1 etc. sigma 2 AWN. Similarly, last row is sigma n AW1 etc. sigma n AWN. So this is the first discriminant or the discriminant in the numerator divided by the discriminant in the denominator is sigma 1 W1 etc. sigma 1 Wn etc. sigma n W1 etc. sigma n Wn. This is the discriminant in the denominator. So when since the sigma i's are monomorphisms, you can write the sigma 1 a W1 as sigma 1 of a into sigma 1 of W1. So and from the first row, here we have, for the norm we have square here raised to 1 by 2 here. So when you split this determinant as sigma 1 of a into sigma 1 of W1, from the first row you can take sigma 1 of a out because sigma 1 of a is common in the first row. In the second row we have sigma 2 of a, this is the square. For the discriminant we have a square. So when you take the sigma 1 of a from the first row, we can get sigma 1 of a square, and from the second row we have sigma 2 of a square. When we take all these common factor out, the remaining will be the same in the numerator and denominator. So this will be cancelled out from the numerator by extracting the sigma 1 of a square, sigma 2 of a square etc. sigma n of a square. Then we simplify, we can get this will be sigma 1 of a into sigma n of a square whole raised to 1 by 2. So that will give norm of the element A. So this shows that norm of the idea generated by A is same as norm of the element A. This is what we discussed in corollary 5.10. So norm of A is equal to the cardinality of norm of the element A. Now we have an example 5.11, or we consider Q of root D as the number field and O is the ring of integers of that. Then n of a plus b root d is equal to a square minus b root d. So norm of 18 can be written as this 18 square. So we can also think that this norm is multiplicative as well. Now we have theorem 5.12. In theorem 5.12, we will prove that norm of AB equal to norm of A into norm of B. So we will prove this multiplicativity property of norm here. In order to prove this n of AB equal to n of A and n of B for arbitrary ideals, we will prove the result n of AP, where P is the prime ideal, so it is as maximal as well. N of AP is equal to n of A into n of P. To prove the multiplicativity of A and the prime ideal P, we will establish the equation cardinality of O by AP is equal to O by A into cardinality of A by AP, and consequently we prove that cardinality of A by AP is equal to cardinality of O by AP. So when you substitute this substitute for this as cardinality of O by P, we can get this is the norm of AP equal to this is norm of A, and this will be the norm of P. So we will first establish this result, then by this, okay, we can get the result. Now We define a homomorphism phi from O by AP to O by A, defined by phi of AP plus X. This is the coset corresponding to X of AP equal to AX. And we will prove that this is a surjective ring homomorphism with kernel AP. So this is very trivial thing. When you consider AP plus X is mapped to, when you consider AP plus x1 equal to AP plus x2, we can get AP, can get AP. AP plus x1 minus x2 equal to 0. What is 0 here? 0 is AP itself. Now you can get x1 minus x2 is an element of AP, but AP is contained in A. Okay, every element of AP is a multiple of some element of A. So we can write this, from this you can write x1 minus x2 is an element of A, then x1 A plus x1 is same as A plus x2. So this implies that this map is well defined. The oneness is very obvious because if you consider any coset of A plus x, we can easily get an x. Then using this x, we can define AP plus x. Then image of AP plus x will be A plus x. So this is always this. Obviously, this is surjective homomorphism. Now we can think of the kernel. Kernel is defined as the cosets AP plus x such that whose image is identity in O by A. Identity of O by A is A itself, so we can write A plus x. This is the image, that should be A. So this set will give the kernel of this homomorphism. So from this you can write A P plus x such that from this you can say that x belongs to A. Okay, so this is the cosets of AP using corresponding to the elements from A. So this is nothing but the quotient A by AP. So this consisting of the cosets of AP using the elements of A. So we can easily get the kernel of this homomorphism as A by AP. So from this homomorphism, using the fundamental theorem of homomorphism, we can write A by AP by the kernel. Kernel is A by AP is isomorphic to O by A. So using the cardinality of this divided by cardinality of this, all are finite, is equal to cardinality of this. You can write, now you can write O by AP is equal to the cardinality of O by AP is equal to cardinality of A by AP into cardinality of O by A. Now we will prove that this is nothing but O by A. Now we have norm of AP is equal to norm of A into this is, we will prove that this is P, O by P. Then we can easily prove that this is norm of A and this is norm of P and this is norm of A. Okay, so once you prove this using the prime factorization, you can easily find norm of this is P you can easily find norm of A, B is equal to norm of A into norm of B. So our next intention is to prove norm of or cardinality of A by AP is same as cardinality of O by P. Okay. Now to establish that result, we start with this. A is always not equal to AP, otherwise you can cancel this A, then you will get this P is equal to O. Since P is a prime ideal, this is a proper ideal, so that never be O, then A never be equal to AP. So, but we know that A always contains AP, but we know that equality is not there, so A properly contains AP. Next, we will show that there is no ideal B which strictly between A and AP. So, whenever you assume an ideal in between A and AP, you can using the inverses, okay, or fractional ideals, you can write it as A inverse A inverse B, A inverse AP follows this inclusion. Okay? A inverse A is this O, and A inverse B is in between this P and O. You know that P is a prime ideal. Every prime ideal is maximal ideal. So we can say that either this A inverse B is equal to O, otherwise A inverse B is equal to P. So A inverse B is equal to P implies what is this B? This B is always AP. Otherwise, A inverse B will be O. That means A is equal to B. That means this implies A equal to B. So whenever we assume a B, then either this B will be equal to A or this B will be equal to AP. So we can say that there is no ideal strictly in between A and AP. This shows that that means there is no ideal in between A and AP means if you consider A belongs to A by AP, you can get this ideal generated by AP plus ideal generated by A. Okay, this A is not in AP, so this is always an ideal which is strictly greater than this AP. So this should be equal to A, because we know that there is no ideal which strictly in between A and AP. Whenever you got an ideal here, that ideal should be equal to A or this. Okay, but this ideal never be equal to AP, because this ideal contains at least one element A which is not in AP. So this always equal to this will be equal to A. So we can write AP plus ideal generated by A is equal to the ideal A. Now we fix such an element A, that A is an element of this A minus AP. Now we define, using this A, define a map theta from O to A by AP. These are ideals, these are quotient ring, defined by theta of x equal to AP plus x. Okay, you can easily prove that this theta is a O module homomorphism, like linear transformation. So theta of x plus y can be written as AP plus A into x plus y. Using the distributive property, you can write it as AP plus AX plus AP plus AY. So this is equal to theta of x plus theta of y. Similarly, you can prove theta of c times x, that is equal to AP plus ACX. You can write it as c times AP plus AX. So this is c times theta of x. So I can prove that this is a O modules homomorphism. Now you can write the kernel of theta from O to A by AP. The kernel is defined as set of all x belongs to O such that theta of x equal to the identity element. Identity element is AP. Okay? Identity element of A by B. So this is set of all x belongs to O such that theta of x is defined as AP plus AX equal to AP. Okay, this is the kernel. When you take P belongs to this ideal P, what is theta of P? This theta of P is equal to, by definition, AP plus A into P. This is always an element of AP, hence this will be AP. So we can say that image of P, okay, theta of X equal to AP. Similarly, theta of P is equal to AP. This shows that P is an element of the set. Clear? So if we choose any P belongs to the ideal P, we can get that P is an element of kernel. So we have this inclusion. P is always contained in kernel. So P is always contained in kernel theta, and which is contained in O. This is a subset of O. Okay, but this never happens. Kernel theta equal to O. Okay, this is not possible. Whenever we have kernel theta is equal to O, we have this A by AP is isomorphic to singleton successor. This implies A by A is equal to AP. This is a contradiction. We already see that this A not equal to AP because P is a prime ideal, which is proper ideal. So this kernel theta never be equal to O. So the only possibility is kernel theta is equal to P. Because this P is the prime ideal, hence it is a maximal ideal. So there is no ideal strictly in between these two. So we can get this kernel theta is equal to P. Clear? Now using the fundamental theorem, O by P is isomorphic to A by AP. Okay, so this shows that cardinality of O by P is equal to cardinality of A by AP. So the result follows. N of A, we can say that N of A is N of AP is equal to N of A into N of P for every prime ideal P. Okay, now if you consider two arbitrary ideal A and B, so this B can be factored P1 into etc. PR. Now we can say that N of A B, this is equal to N of A into P1 etc. PR. Okay, so this can be written as N of A into P1 P2 etc. P1 P2 etc. PR minus 1 into PR. Okay, so this can be written as N of A except P1 etc. PR minus 1 into N of PR. Okay, now you can extract all these N of P1, N of P2 etc. Then this will be N of A into N of P1 etc. N of PR. Okay, now you can regroup this again since these are prime ideals. So N of A into N of P1 P2 etc. PR. P1 P2 etc. PR is nothing but B. So we can get N of A into N of B. So once you have proved this theorem for a prime ideal P, then you can prove it is for every arbitrary ideal B. So N of AB is equal to N of A into N of B. Next is an example. You can find norm of the ideal generated by 18 using this property N of P1 square, P2 square, P3 square, that can be written as N of P1 whole square, that is 2 square, 3 square, 3 square. So then that will give 18 square, which is the norm of ideal generated by 18.